Our third feature of NMR has to do with the ratio of hydrogens in a molecule that are non-equivalent to each other. And this has to do with the peak area. So if we look at the area under these peaks, that will tell us the ratio or the proportion of these kinds of hydrogens in the molecule. So let's say this has the biggest peak area. It may not, but let's just say for our purpose, this has the largest area. If it does, then that tells me this signal corresponds to a larger number of protons in the molecule relative to these guys. Now the neat thing is that these peaks, if you zoom in, you see that there's width to them. So it's not just about the height, there's also a width to take into consideration. So that's why we use area as opposed to just height. But the height often also tells you a little bit, because they're not really they don't have a lot of width, so you can sort of go by height a little bit, but you really want to rely on the software to give you these integration curves. So integration is the area under a curve. The computer will calculate these for you usually. Otherwise, you can use other methods we've learned before, like for GC, we learned how to use the triangulation method or how to cut out the peaks and weigh them to get the approximate ratios. So here, the computer will give you these integration curves. Usually how we use these integration curves is, you see for this one here, this is a nice step curve here. So we basically look at these two lines down here and we measure the distance with a ruler, and that gives us a number. Let's say it's like 40.2 millimeters or something, okay? Now this one here, you can see the step curve sort of tries to break it out. So this peak here has this integration, this peak here has this integration, and this last peak of these three peaks has this integration. Or you might just think of this whole thing as one big signal because it's all coming from equivalent hydrogens. And you do the same thing. You sort of look at this distance here. So clearly this is smaller than this one. This is 27, this is 40.2. All right, so we do the same thing over here. So let's just look at the distance here. I measure with a ruler, maybe I get 28.4 millimeters. Over here I do the same thing. Okay, so that's how I could do it manually. If the NMR gives me the curves, then I take out a ruler and I measure these distances. Or the computer may actually give you those values, the ratio of values, without any particular unit. And once you get those values, those are the integrations, you want to turn them into whole number ratios because hydrogens are whole. We can tell whether we have 6 hydrogens or 2 hydrogens or 3 hydrogens. We usually don't say we have 1.56 hydrogens, right? So you take the smallest number, which is 27 in this set, you divide every one by 27 and you look at the ratio and you see if you have whole numbers. And if you don't, then you multiply by a factor to give you whole numbers. This is a typo here. This is 1, obviously. Okay, so 1 to 1.5-ish to 1-ish to 1.5-ish, right? So you can just sort of play around with it. It's a lot like when you did empirical formula in Gen Chem. You remember you divided by the smallest number in moles and then you got the lowest, simplest mole ratio. Okay, so it's a lot like empirical formula calculations. So anyway, we're basically saying that we have if I multiply all these by 2, I have a 2 to 3 to 2 to 3 ratio. So I'm going to take all of these, multiply by 2. So that means then I can go back to my NMR spectrum and I can say, oh, this signal corresponds to 2 hydrogens that are equivalent to each other, 3 hydrogens that are equivalent to each other, 2 hydrogens that are equivalent to each other, 3 hydrogens that are equivalent to each other. All right, okay, so that's really cool because now I can start looking at molecules and see, oh, here's the 3 hydrogens that are alkyl, or here are the 2 hydrogens that are in the alpha position of a carbonyl containing group. So anyway, this will be really, really useful. Let's look at 3-pentanone, okay? And you see there's 2 signals, meaning there's 2 non-equivalent types of hydrogens. And I think we know there's these hydrogens here, H2, so that's one type. And we see H3s here, so that's another type. So, and I'm not drawing the carbons, but So these red ones and these blue ones are going to give basically two types of signals. Now, which signal is for the red hydrogens and which signal is for the blue ones? That depends on the shift. We need to know about the shift now. Who do you guys think, the blue or the red? Which hydrogens are going to be more upfield? Or conversely, you could ask, which of these hydrogens will be more downfield? So not really needing to know much. I know the oxygen is pulling the electron density, right? So I know that these are going to be more de-shielded. So that means these hydrogens are the alpha carbons. And so there's should be a 4H integration here because there's 4 equivalent hydrogens giving the signal. And then these guys are farther away from the oxygen, so they're going to be more shielded. So that, and there's 6 of those, so I'm going to say 6H over here. And sometimes people draw a little curve here just to mimic what the NMR software does. So anyway, the actual values provided to us are 32.5 and 48.0. Go ahead and see if you could take these numbers and verify that we have a 4:6 ratio or a 2:3 ratio, more simply. Oh, and that's a good point, guys. We usually simplify these ratios. So instead of 4 and 6, which you're not really going to see, you're going to see 2:3. That's just the way we always report the simplified ratio. All right, guys, so to verify the integrations, I'm going to divide both of these values by the lowest one. So 32.5, this sets this equal to 1, and that sets this equal to 1.48, which is about 1.5. So if I multiply both by 2, I get 2H and I get 3H. So that makes sense for integration for this molecule.